Live? Yeah, yeah. Okay, let's get started. Welcome everybody. We are delighted to have Professor Madhu from Harvard University visit us. Madhu is a frequent visitor to TIFR, more frequently than some people know. It's the talk rather than you. The talk is very, it's a nice talk which I heard the conference version of it a couple of months ago. It's about the problem that several of us possibly face. You're working on a problem based on what your advisor has given you, and then which in turn is what their advisor has given. I mean, you do something, one, to realize everything you've done is correct, but the result falls apart because somewhere along this chain of advisors, one of them has lied along the way. So this is a model to catch a probably lying advisor.
It's where the fault always lies.
Is this correct? Let's check.
Okay, thank you very much, Prahlad. Thank you all for coming. It's always a pleasure to be back here. See the mix of the old and the new, including the rolling green board, which still exists. Quite amazing. I think I first saw it like about 20 years back. So it's quite impressive. And I know it's much older than that also. And yes, like Prahlad said, this is a story about errors and sort of how to check for errors in a somewhat new context. So the general thing that it bothers me a lot is, there's a lot of information that is built up by society. There's societal wisdom, knowledge that we all have collected over the years. And a lot of it is cumulative. It builds on top of each other, all these pieces of knowledge which are building on top of each other. And what's the process by which we build elements of knowledge? We collect data, we analyze it, we prove theorems, we use other people's theorems to prove new things, we look at other people's data analysis to build inferences on top of that. And every one of these processes is, of course, prone to noise. I mean, all of us who sort of worked on things like probabilistically checkable proofs and so on, we make errors in papers on probabilistically checkable proofs. So it's a common phenomenon that, errors happen. And it's even arguable that if we decided not to be somewhat allowing of errors, then we would make no progress at all. I mean, we would be so conservative and cautious that in general, we may not be making progress at all. So societal knowledge is built on very, very, very noise-prone ingredients. There must be some methods out there which check for errors. What are these? Okay, and help us correct errors. And a few things that are probably sort of familiar to some of you. We worry about errors in communication, so we have error correcting codes. Many of you have probably seen about them or heard of them. We worry about errors in our derivation and knowledge process. So we sort of built this mechanism of writing proofs, which are meant to allow other people to verify our claims. Okay, proofs are a very, very big factor in allowing knowledge to be passed on with some, addition, with some noise tolerance. When I'm first coming up with a proof, I might have it wrong. By the time, it needs to be used by many people, the proofs better be right. But, these are very sort of extreme mathematical settings. The common setup of human knowledge is not so rigorous and so rigid, but there's this generic thing of, information passes. As you pass it, you sort of maybe put in some new additional things on top. And then maybe we have some method by which we can sort of check some very local things. Okay, something was published in the newspaper day before yesterday, something was published in it yesterday. Is there a contradiction amongst these two? We can try to look for it. But it's not as if things are going to follow from the axioms. And by the way, very few things that we reason about, even in mathematical knowledge, actually follows from the axioms. The axioms are far, far away, lending us a foundation and support, but we actually are so far away that we can't even see them. So we definitely use this all kinds of sophisticated means to build on knowledge, to communicate knowledge, and also to correct some of these things. And today we will try to talk about some very basic elements. But I'm really very curious. I mean, other than error correcting codes, proofs, and things, are there other ingredients that allow us to be robust? What is it that allows this, very complex infrastructure of facts building upon facts, not fall down completely and have most of the things that we are knowing completely erroneous but stable? And there are very interesting things like multiplicative weights or boosting as a method by which you can sort of learn lots of very, very weak hypotheses and then integrate it into a very strong one. These are very interesting mechanisms. Today, I'm going to look at a very simple probabilistic process related to this. And it's one step in a hopefully a longer sequence of things. And it's going to be said, there's very little computation. There's no computation in this task. It's all basically just a simple probabilistic model and how to analyze it. Mostly, I think what will come out is, lots of interesting questions that maybe others can follow up on. Okay. So I think Dan Michelschiner, so the co-authors on this work are Omri Ben Eliezer and Dan Michelinser, who are both postdocs at MIT right now. Elkaran Morsel, who's a faculty there. And I started this work when I was on sabbatical there a year ago. And we've been sort of thinking about related topics ever since. So Dan put in this slide about Lebesgue having this paper, which was published as a theorem in 1904. And this paper seemingly has 303 citations. Okay, so lots of people apparently built upon this work. And some of these are prior to 1917. And in 1917, somebody actually found an error in this thing, and this theorem is no longer true, or whatever. I don't know exactly whether the theorem is not true or just the proof was false. And by the way, this paper, which I think we're looking at it, doesn't have as many citations as the original one. So, you do have this very interesting thing saying, oh, look, all of these people are still citing that mistaken paper, and this error could be propagating. And how many of these people might have been cited by others? And mathematics is not the worst terrain for this. If you think about, So mathematics is not the worst terrain. I think there are sort of zillions of examples in biology and physics, and wherever you do data analysis, and you will have conclusions saying, eating fat is eating eggs is sort of absolutely bad for your health was the conclusion from 30 years back, and 10 years back, it was sort of turned on its head. So it's the most healthy fat. If you're willing to eat some amount of fat, this is the most healthy thing you could eat. So things do keep going back and forth in this knowledge domain. So how do we work with this? Okay. So what we are going to do in this in this talk and what we did in this paper is to build this up as a simple probabilistic process. So in this process, we will have new units of knowledge, which will be simple nodes in a graph. We will have no deep we will not try to go deep and understand what this node is actually saying and how does it relate to other nodes in the graph. It's simply a factoid that we just found, a new unit of knowledge. And then it will have links to saying, oh, I depend on this piece of knowledge and that piece of knowledge and that piece of knowledge. So this process will evolve somehow. And as this evolution happens, there may be errors introduced. So some piece of node that was introduced claims to follow from these three other things may not actually follow. So what happens when you start having these kinds of errors? So, and now if anybody relies on this fact, even though they did their derivation properly and correctly, it's going to be wrong because they're depending on something that's incorrect. So this process will keep propagating forwards, but then maybe somebody can come along and notice that, oh, this paper said it depended on these three, but it doesn't follow from it, or in fact, here's even a counterexample, etc. It may be an error may be discovered later and then eliminated. And then there may be some process by which you eliminate other errors. So in particular, if I say, oh, look, I'm going to read this paper and this paper is dependent on that paper. And oh, look, there was an error in this particular derivation. Then I can also go tell the errors of the intermediate paper, the authors of the intermediate paper that their result was also wrong, and let at least nobody cite this one any further. Yeah. So these are the things that we want to model. So let's set up the model carefully. So the ideally knowledge should be stored as a directed acyclic graph. You start off, the root is, the axioms, and then you start developing new theorems or units of knowledge from it. We don't care how and what. And at each time step, we sort of come up with some new unit of knowledge. And these edges will be representing, what is the dependence. So if a new knowledge depends on 3 previous things, then there'll be arrows coming from the previous things. Okay. And the one catch, unfortunately, is we would love to talk about the setting where every paper can cite a bunch of other papers. But we would not ready for a very deep dive into the structure of knowledge. And sort of it's ridiculous to suggest that we will, I will cite 3 random papers that have been published previously in scientific journals or mathematical journals. I mean, there won't be 3 random independent papers. They'll probably be correlated and somehow structurally together. So we wanted to get back to this thing of, okay, every paper can depend on multiple papers, but for this first starting expedition, we decided, okay, let's ignore this. We will just have each paper depends on one previous thing. Let's keep it very, very simple. I mean, I think people do study propagation and, errors and disinformation, misinformation, et cetera, et cetera. And most of the study is every paper depends on 0 previous things. So I think we're at least making a step forward by saying we're depending on 1 previous thing. Okay. 1 is not the best model, but unfortunately, that's not a DAG anymore. So our knowledge is going to be represented as a tree. And the tree starts off with some nodes. And as they propagate downwards, they will say, look, every new node comes along and say, it'll choose a parent. And on that parent, its truth will depend on the truth of its parent, and of course, on the truth of the new step of derivation. Okay. And so in each state, we will put in a hidden thing saying, was the latest step of derivation correct or not? And we label this by, I think the important thing is being conditionally true is the correct phrase to focus on. A node can be conditionally true. What does it mean? Well, if its parent is true, then it's true. If its parent is inherently false, then this node is not false. Just to stick with the same notation, we will say, well, the node could be born as just conditionally false, but this is a hidden state. Nobody knows that this node is true or false yet. It may be discovered at some later stage. Okay. So when discovery happens, which will be later, they decide that, okay, nodes will be proclaimed true or false. At birth, every node will be proclaimed true. But even at birth, you might say, okay, look, I just came up with this brilliant idea. I'm going to publish this theorem, but let me just make sure that I actually am, I might do 1 round of checking before I actually publish my paper. And I might also check one of my antecedents or something like that. So along the way, I might actually, even at birth, I might decide to say, oh, okay, actually, the latest step of derivation was not correct, so no longer true. I might proclaim myself false. This is a kind of a minimal, uninteresting event. But other people, people could be reading your paper and your relationship to your antecedent and realize that there is a gap in between and later proclaim you to be false. That's the more interesting event that we are interested in. And when you are at birth, you have to figure out who your parent is going to be. Okay. So this is one of the things that we want to understand. So at time t plus 1, so at each time t, we will have a knowledge tree saying these are all the facts that we know. Some of these have already been proclaimed false, announced, published as papers, but then withdrawn and retracted. So we don't have to worry about them. And so when a new node is born, it will choose a parent amongst the ones that are actually proclaimed to be true. These are not necessarily true. There can be some hidden, undiscovered errors in these papers, but only the ones that where the errors are undiscovered, not the ones which have already been discovered. But also a funny thing could happen. My parent might have been false for some reason. And later somebody came along, tried to tag on, build a new theorem on it, and realized, oh, the parent is false, and sort of declared them to be false. And now but I wrote the paper, I thought it was true. Nobody has actually written a retraction for my paper, and I haven't been told that this parent's paper is false. So it's not as if as soon as a node is proclaimed false, all descendants are going to be declared false. This is not necessarily what happens in the literature. What happens really that we see is people realize that their paper is an error. They might publish a retraction. They might tell some other people about it, but that's, very rarely does it actually get propagated downwards. So there could be one paper was false, led to some bunch of follow-up papers. Some of them over time discovered as false because they depended on these false things. Others are still carrying on and merrily marching along. And everything in the subtree is from now on false. And we might have to figure out what happens. Now, how do you choose a parent? And for this, we chose the sort of one of the most popular models in this kind of universe. You sort of the rich get richer model, the preferential attachment model. So if at time t, we have this tree T sub t, some of its nodes are proclaimed false, they're out of contention. Amongst the remaining, you look at, you choose a parent with probability proportional to their degree, or really 1 plus their degree, because at birth you have no children, so 1 plus the number of children. Okay. Probabilities for this proportional to that. So people that are very popular in the early, an early paper will get many more citations in this process than later ones. But once you start building up many citations, then you will get more and more. Okay. Does this make sense? How many people have seen the preferential attachment model before? A few of you, and not enough. So if anybody has questions, and by the way, anytime you have questions, you should definitely feel free to ask. Okay. So,
so when you mean labels there, what are the labels? Is TFPT, TFPT, or
no? The only label given to you at birth is a hidden label of conditionally true or conditionally false. Okay, so
what is it hidden from?
Hidden is in order to be okay, good. So think of this as a following: a node is born, has a label on it, and it's sealed. And then somebody comes along and checks this node. At that time, they'll open this label to see is its hidden label. What is its hidden label? Okay. So the initial label is always conditionally true or conditionally false, which says conditionally false is actually unconditionally false. It is just false, but it's not been announced as false. This will be revealed as false later on. But you could be false for other reasons. Other reasons are that one of your ancestors is false. Okay. And initially, all of these are going to be hidden. But over time, we will also have an announced label. I mean, at all times, the announced label is whether you're proclaimed false or proclaimed true. This, you can just imagine that everybody who's at birth is proclaimed true. Only later do they get, somebody opens this thing and checks, and then that's...
proclaimed false doesn't percolate.
Does not know. Percolation, we will tell you exactly what will happen. So let's, so errors are being introduced by saying things are either proclaimed true or false. And what is the probability with which every node has, will toss a coin, which is biased. With probability epsilon, it will land heads, and then they will be proclaimed false. With probability 1 minus epsilon, it will be proclaimed true. Conditionally, they will be conditionally false with probability epsilon, and unconditionally and conditionally true with probability 1 minus epsilon. There was a question here.
Yeah, so something like this could happen, right? That so some chain of nodes were all conditionally, like the hidden state was they're all conditionally true, and then let's say the leaf node here was conditionally true, but now it's proclaimed false, which means everything above, or at least that it should start propagating proclaimed false upwards.
Okay, good. Let's find out how the sort of announcement of proclamation, the checking will happen. We'll get to that in a minute, but not exactly what you're suggesting. Okay.
So you're also going to tell us when does one open this?
Yes, exactly. That's going to be this error checking process that we have to. So there's the growth of knowledge, there's the injection of errors, and there's the checking of errors. We've talked about the growth of knowledge. That's just how this tree is going to grow. You're going to attach to a node which is proclaiming to be true and with probability proportional to its degree. How do errors creep in when you're given this label of conditionally false at birth? That's an error. There is other errors, which is just because of propagation. If anybody in your ancestor chain is conditionally false, that's an error. Now, what about, so there is this parameter epsilon, which is the probability of a thing, and this is going to be one of 3 parameters associated with our entire model. So this is the first one.
So when you say that growth proportional degree, does that it only includes the proclaimed true degree?
Only include, no, sorry, only includes the proclaimed true degree. Absolutely, sorry.
Height was not there, the degree would be 0.
So this guy has degree 2 right now because all the others are, oops, sorry, these are conditionally false. Now, we don't say what's proclaimed false or true, but suppose we pretended these are all proclaimed true and proclaimed false. Then this would have degree 2, this would have degree 1, this would have degree 1, but we wouldn't, yeah, if it was proclaimed false, we wouldn't attach to it. Yeah. But this, and notice that everybody gets 1 plus their degree, so that even this node can have a child that will be with probability 1. Even though its parent is false, this is proclaiming to be true, we don't necessarily find out about that. Okay, let's find out how we find out about errors. Yeah.
So I'm just trying to, what should I think of as the semantics of something being conditionally true? Should I think of it as saying, assuming that my parent is true, the derivation I have made is correct?
Exactly.
That's what I
Conditionally true really means what it says.
Yeah.
Conditionally false means the opposite, unfortunate choice of terminology.
It's totally legit to have a, like you have conditionally false node that have children which are conditionally true.
Yes. And the way this might happen will depend on our checking. How do we, so certainly the growth can go look like this because everybody right now might be proclaimed true. And so we don't really know this is the exact tree. But at some later point, after this person had a child, somebody might come along and realize, oh, this one is false. And so we might stop them. Now, okay, by the way, this is, I think, I mean, I heard this from Elkhanan. And, probabilistic models are just too simplistic to be actual reality. Okay, so they're all wrong. But some of them can be actually insightful. And one of the things that we are trying to find out in this case is, what kinds of error checking models could be plausibly feasible and sufficient, which ones are really bad ones, bad ideas. And so maybe there's, you should look at the lessons and then take them with a grain of salt. So we are developing a model, we try to keep it simple and clean and hope that it captures some things. So checking for errors. Okay, now we come to the key question. So whenever a new node happens, okay, so this is the general model of how we are going to, oh, sorry. Okay. Yeah. Okay. So whenever something, we don't go around just willy-nilly going around looking for errors in random papers. Okay. So the assumption is we check for errors because we might be interested in this particular thing. And so if I'm looking at a new node, I'm saying, oh, look, here's a nice theorem. I could maybe try to use this and build a new theorem out of it. We could make the model which says, okay, let me go check this theorem and all its antecedents, go all the way up and check. But, if knowledge is getting very deep, this is going to be a lot of time checking. So we want to suggest that, look, your goal is to get the payoff, a new node, a publication, and you don't want to spend, 1 in n of your time publishing your new thing and n-1 out of n checking a tree of depth and saying, oh, look, is this correct? And is that correct? And is that correct? And is that correct? So what is reasonable is you check the last few nodes maybe. And or you could even do other simple things like, take an exponentially distributed random variable or check your parent with probability 1/2, with 2 parents with probability 1/4, 3 with probability 1/8, etc., etc. You could do some things, but you go up some distance in expectation a constant number of steps, and you check them. And again, depending on this may not be a purely random variable. We model it as a random variable. With probability p, you decide to do a check. With probability 1 minus p, you do nothing. You just, you found the new paper, you just publish it. So you may be conditionally false, all kinds of other things could be wrong. And with probability p, when you decide to check, you check a certain number of levels. This could have been a random variable. For simplicity, we kept it as a deterministic. It's a parameter of the system called k. We are going to check k nodes up in the tree. K is to be thought of as a constant. K, p, and epsilon are the 3 constants, and they completely determine nothing. When you check somebody, if they're false, conditionally false, you reveal that exactly. And if they're conditionally true, you reveal that exactly. But if you're conditionally true, you just sort of announce that they're still proclaimed true. If they're conditionally false, you announce that they're proclaimed false. On the path that you checked, you mark all the nodes that are discovered to be false by inheritance also as false. But you don't go up, and you don't go to all their siblings and their further descendants. Okay, so constant amount of work per person who's doing the checking.
This happens at the same time the node is.
Yes,
So when you publish your paper, you do this extra.
exactly, and you're only doing it along the path that you care about. Okay, so this is sort of enhancing this preferential attachment world. If I care about a result, then it's more likely to be checked. So in preferential attachment, for example, if I start a tree with 1 node and then grow it to have n nodes, the root would have degree about square root of n. The depth of this tree will be still about roughly log n, but the root has very high degree. Square root of all the things are immediate descendants of the root. So the root must have been intensely checked. And so we can be pretty confident this is definitely going to be true. I mean, all of the children must have chosen not to check, and all of the children up to level k must have chosen not to check in order for the root to be still true. But, it could happen that something's happened. Okay.
So just maybe rephrasing the thing, because of the preferential attachment model, nodes that have more children are more likely to be correct.
Exactly. Because of this preferential attachment model and because of the way the error checking has been defined, if nodes have lots of children, they're very likely, and in general, level K descendants, if you have lots of them, you're very much more likely to be true. But that being said, I mean, the tree is also growing, and maybe there's people who have lots of children and descendants, but the union bound says such a structure can also exist. Okay, so anything could happen with positive probability, and if you're taking the union over enough events, independent, etc., then one of the
Preferential model only biases the factor degree to have even larger degree.
exactly. Yeah.
But condition on the fact that degree is D, the probability of thing we discovered doesn't depend on the preferential.
Exactly, that's right. So it's not so much the preferential attachment; it's the growth is the checking process, which says that when you had a child, the child had some probability of checking you. So if you have lots of children, then you must have been checked lots of time. There were lots of opportunities to check, and so very likely, the conditional probability says they're very likely true, but what means, yeah.
There are no errors in the checking process.
There are no errors in the checking process. Good. So a couple of things. I mean, these were in many of these things when we started thinking about it, we said, oh, look, during the checks, should there be errors or not? We said, oh, look, why have 2 parameters? There's P, which can be thought of as the probability of a correctly checked process. That would have been correct, but it also sort of introduces some monotonicity in our tree. It's not possible that, if I've decided to check this depth K thing, it's not possible to miss any conditional false over here. If I discover a conditionally false node over there and there was another one in between, I definitely will also discover it. I don't know that, we needed to have the checking done in this particular way, but, we just chose to do it. Yeah. So we just said, yeah, when we check and we get the right answers, but it's a reasonable thing. I mean, I could have just scaled P down and had a different thing saying this is the probability with which you checked correctly. Good. So that's the thing. So checking for errors happens. Whoops, what is this thing? I don't know why I have a it's very strange. So converting PowerPoint to PDF led to some further errors. Okay. So there's probably new models for injection of errors that we are introducing as we go along. Okay, so that's the whole model. It's what we call this epsilon PK cumulative knowledge process, and we want to understand some questions. So let's see what are the kinds of questions that we want to understand.
So can you just comment, what are the three parameters? So
Good.
epsilon,
Oops, sorry, it takes time. Epsilon is the probability that a node is conditionally false.
Oh,
At
okay.
birth, it's error. So the error is epsilon, and P and K are the checking. P is the probability with which I check, and K is the number of nodes that I go up. So what was very initially, the following is possible. I could even have a process in which epsilon is 0, okay, just for, we could, and the only point, so epsilon 0 means no new error happen. The only error in this whole system is the root. Okay, the root just happened to be a conditionally false node. And now we are starting to grow the process. Okay. At the end, what should happen? If there is justice in the universe, everything in this tree should be at some point deemed proclaimed false, and there should be no further growth. From now on, it cannot. If everybody is false, then you cannot have any children. But it's possible that this is not going to happen. There is maybe a tiny probability that this node has a lot of children before they are discovered. By the time they're discovered, all these children have children, and children have further children, etc. And this keeps growing. Can this possibly happen? Okay, so so we thought this would be the simplest questions to understand. Can this process ever lead to, if epsilon is small? And of course, if P is 0, I never check, then this process goes on forever. No, there's nothing surprising about it. But what if P is kind of small? Will we eventually always discover errors and root it out? For what kinds of values of P and K is it the case that this process will never be discovered? And whenever we say, okay, if once P and K are slightly positive, K is positive, K is at least 1 and P is slightly positive, there's always a positive probability that the first node that is born will check the root and say it's false and it dies, the whole system is gone. So there's always going to be a positive probability that this system will die. The question that we should really ask is there also a positive probability with which the system grows on for infinity? Okay, and that's really the right kind of question. Those are the questions that we will. Yes.
Question, even for epsilon equals 0, your question is there a P and a K for which there's a positive probability on an infinite tree?
Exactly. Yeah. And in particular, P greater than 0. When P equal to 0, yes, it will live forever. P greater than 0, K at least 1, what happens? Okay. Now, so sorry, I confessed earlier to Mrinal that these slides were not prepared by me. I am just making sure that I'm reading them with you. Right, so let's go to the theorem. So here is the interesting theorem. This is the first interesting theorem. So if case is 2, okay, so you're checking your parent and your grandparent, then for every P less than 1, in fact, I think it even includes P equal to this error effects are going to survive with positive probability. So if you're just killing, if you're just checking 2 levels up, okay. And why is this the case? Well, remember what is our model over here? We are looking in the case where epsilon is, so the result holds for all epsilon, but In particular, it holds even for epsilon equal to 0, where only the root is thing. So how are you ever going to discover an error? Not because you opened somebody and found them to be conditionally false, because they're not. Everybody is conditionally true. But because you actually touched upon a node which is conditionally false. So just checking your parent for errors is not going to do anything. If there are an error, you will at birth decide not to be born. If they're not an error, you'll be born. So you're never actually, if somebody who's born and is false is never being eliminated if k equals 1. Okay. So that's completely uninteresting to study. K equals 2, what happens is you born, you check 2 levels up, maybe, with some probability, but some probability less than, sorry, I think this is every p less than 1 is correct, yeah. So with some probability, you forget to check, and so you end up having being born. And then after a while, somebody comes along, tries to attach to your parent, and then goes up and checks, and then realizes, oh, your grandparent was actually false, so your parent dies. Now, after a little while, somebody tries to attach to you, checks you and your grandparent and your parent, and realizes the parent is false, and so you finally get eliminated. So there is a positive probability that you can get eliminated in this process after being born successfully. But it turns out that with k equal to 2, you actually, the expected time before you actually get a newborn node, a leaf is eliminated. By the time a leaf is eliminated, it turns out it's produced many new leaves, and this process keeps propagating. Okay, so depth actually matters. If you are checking only 1 or 2 levels up, it's not going to be enough. You should at least check 3 levels. On the other hand, so let's see, I think this is statements of the theorem. So I will go on to the next thing. If you're checking at least 4 levels, for every epsilon, there is a probability of checking. So for every epsilon less than 1, there is a probability p0 less than 1, such that if you are checking with probability at least p0, then the error effects are eliminated. And if not, these things will survive with positive probability. Okay. So beyond level 4, we are in sort of decent shape, and up to this thing, we are not.
So
Yeah.
the way I have interpreted this is that when you say that it survives with positive probability, it means that there is a node which is erroneous, and then there is a path that it produces keeps producing children forever.
It's,
there is a subtree.
no, every node will die with probability 1 after some time, because as long as k is greater than 2, greater than equal to 2, every node will die with positive probability after some time, because your parent will die with positive probability by induction after some time. And once your parent is dead, at some point, somebody will come and try to check them, and and this is going to happen infinitely often. So you will die. The question is, by the time you die, have you created so many new children that the entire, all the nodes should have been proclaimed false at some point, and it hasn't happened. You die, but some children or descendants are still surviving. Your descendants are surviving. Any descendant you pick, that one dies eventually, but its descendants are surviving, and so on. Okay. Thanks. All right. So, the moral of this story is that if the checking process is not too shallow, then with high enough checking probability, you can root out it. So you can root out all the false nodes. Oops. So there's some ideas of the result, but let me not. Oops. Wait. So there's one result over here that I really wanted to talk about. Seems not to be included. Maybe I'll. Okay, so let me give a couple of ideas of some of the proofs, and then
So can we just go back to the 2 statements and maybe a little confused. So if k was equal to 2, what was the situation? So like the tree will always survive.
Yeah,
Like says that there is a positive probability with which the tree will survive.
exactly. There's a positive probability with which it's always, there's always some node which is proclaimed true.
Okay, but if K becomes 4 or something, then depending on your epsilon, there is a choice of P naught such that if the checking probability was less than P naught, then your
Then
tree
P.
survives with positive probability.
Exactly. And if checking
And if
probability
probability is more than P naught, then the tree will eventually be eliminated.
will be eliminated. Exactly. Yeah. Okay. And let me say a few things about there was an interesting effect, which was that if P is less than something like a fourth or something, the probability of checking is less than a fourth. Okay, it's not reported here. Let me add this. So another result in the paper is if P is less than 4, something like this, I think it's less than a fourth, then even K equal to infinity is not enough to eliminate.
K equals infinity, you check all the way to the root.
You are checking all the way to the root, and it's still not good enough. Once again, it's sort of this. So you really need to have a sufficiently high probability of checking. You also need to be sufficiently deep. And once you have both of them, then you're working out okay. So, I'm sorry.
This is regardless of what text.
This is true for good. What kind of epsilon is this? Yeah, that's a good question. I sort of forget. What was the epsilon? Oh, no, sorry. This is okay, good. Epsilon equal to 0, root is CF. That's all. So even the simple process. So really, I mean, this is, you would have thought this is the most minimal thing. One node, there was just one false. I mean, and it's, you can sort of think of it in a more general context. And, you had false nodes, true nodes, false nodes, true nodes. Some conditionally false node appeared. Now you'd like to understand what will happen in the future. There was some epsilon which was positive, but it's that's only making the situation worse than epsilon equal to 0, in the sense that more errors are happening. And even with this epsilon, which is positive, this one node, its after effects will never be eliminated. It's now going to survive. With positive probability, it will survive forever. So what does it mean about things? There are many, if epsilon is actually positive, there are many cases where you're going to have some conditionally false node. Each one has a positive probability of having an infinitely many descendants. So many of these are going to actually have infinitely many descendants. Now, in terms of the kinds of questions we really wanted to understand in this paper, this was just the sort of opening thing. We really wanted to see sharp transitions in this behavior, saying, okay, look, up to this point, for epsilon p and k, for every epsilon p and k, either the process goes to, it's clear that, we will either eliminate all error effects or they will survive just by definition, but here is a criterion by which something would happen. Or we would have liked to say that, look, let's consider the, relate some of these processes to each other. One in which the root comes up. So let's start with a process in which the root is conditionally false. Another in which the root is conditionally true. Let the two of them grow. Can you say something about the relative sizes of these two processes at time n? Okay, there should be, the thing that started off true should have many more true nodes in it. But is that sort of polynomially more? If this is going to die out completely, then obviously, this is dead and that one is alive. So great. But if it's not happening, then, maybe it's still the case that this is growing much faster. So these are questions that we would have loved to answer, but we have not been able to answer this work at all. So there's sort of a ton of questions along these lines that we would love to answer.
So, yeah. So P equals 1, K equals infinity, you will realize the root is false.
Yes.
So is this 1/4 sort of?
Beyond a certain point, and I forget what the exact number is, if P is sufficiently, so
It feels like if P is bigger than half also you probably start.
then
To me, it somehow felt like the threshold should happen at 1/3 because it feels like by the time I check my parent, if I have two siblings, then it feels like I mean, this tree is not going to die.
no, okay. So good, great point. So you're saying, look, if I started off, I was a single leaf. By the time I die, I have two children. Then this is a branching process which is going on forever. It depends on the structure of these folks, right? So it depends whether these two children, like if I have one child which has another child, if it has two children in parallel, etc., etc. So at the end, okay, in fact, let me tell you about some of the potential functions that we were able to analyze. So all of these results come from various potential functions. We just say, so
Can I just ask?
yeah.
So you had something. No, so this P less than 1/4.
Mhm.
So you don't know therefore whether this is tight, right?
No, this we don't know that it's right. We know that there is a sufficiently large P beyond which there is a sort of a trade-off between P and K, and now
So K equals infinity, do you know that some P less than 1 works or?
yeah, for K equal to infinity, I mean, I don't know if P, it might be, I mean, we certainly know there is one P which works.
So P equals 1 works, but is there any P less than 1?
Yeah. So K equal to infinity is good for us, right? We even know, for instance, like K equal to 4 and P equal to 6/, I don't know, it was 6/7 or something like that, then we are in good shape.
And this 4 has nothing to do with the other K equals 4.
This is nothing to do with the other K. So, no, yeah. There is a general threshold on PK being sufficiently large. Would usually mean, means the following actually. So your configuration really looks like this. So a bunch of constant size components, but there can be a large number or a small number. If PK is, the product of P and K is large, then essentially what's happening is like this thing in game of life, you see that, you produce a kind of collection of layers which are sort of constantly propagating outwards, but there's nothing in the core, is also vanishing as it goes along. It's more or less like that. So there's some, the start happened, there's no deep paths of connected paths of errors. But by the time one node dies, it produces 1 or 2 children, like you're saying, and then dies, and then produces 1 or 2 more children, and then dies. And this can keep happening. Okay, you can eliminate it by picking K, which is sufficiently large, which is at least I think some. So if PK is greater than some particular threshold, I don't remember what it is, and K I don't remember some further conditions on P, absolute value of P, just to make sure that we're not in this regime, then we are in a shape where we can actually make sure that the small nodes also get eliminated, and then we're in good shape. Yeah.
PK is product of G times K. Is it invariant for it?
It seems to be some sort of an invariant, and it makes some sense. It's the number of kind of checks we are doing per in expectation. So it's a good invariant. And we really thought at the beginning that, we would have a condition on PK and that's it. But it turned out that actually there were some extremal values of P and extremal values of K, which are not good enough. So for K equal to 2, for instance, even P almost 1 is no good. And for K equal, similarly for P equal to 1/10, K could be infinity and it's no good.
Do the results also work in, change the model a little bit in which you do this geometric checking, it's not K deterministic, but they check so many parents based on this one, and there's an expected number of PK is sort of the expected number of parents you check. Is that the?
So we never analyzed those other models, but the general, okay, either we get perfect understanding, but we were so far from it that we gave up on that thing. And then if you're just looking for qualitative extreme behavior, when P and K are very, very large, then we would like to say that things die. And when P and K are very small, we'd like to say things survive. Then it doesn't matter really whether you're at this qualitative stage, it doesn't matter whether you're thinking of K as a random variable or thing. You can just think of P and K being random variables such that with very high probability, P will take on the value at least 1/2 and K will take on the value at least 1/4. And if in this case, the whole thing dies, then, also in our expected thing where same thing is happening, so one of these processes dominates the other. Yes. But those are the only kinds of inferences you can draw, and we don't explicitly draw those things. So I'm almost out of time. So let me just say a couple of words about the kinds of analysis. And it's not very deep, so but let me say a few things. In general, some potential function. And we try to prove that it grows in expectation at all times. And if we can show that this happens for some choices of P and K, this implies that the process lives forever. Or if you can show that it shrinks in expectation at all times, then process dies.
So here grows and shrinks refers to the potential function.
Yeah. And potential function, this thing. And the question is, what kind of potential functions work? So one nice potential function was just sort of something like number of leaves in the thing. Okay, so this is easy to analyze because, at any one time, how many leaves can you kill? You come in, you either add one new leaf because you're a leaf or something, or you might go attach to a leaf, and then maybe you decide to, but you survived, and so you didn't make any changes, or you attach to a leaf and you kill it or something like that, and because you decide to do some checking. When you do some checking, you kill at most one leaf. You don't, because all the other things you're killing are ancestors of this leaf. So the amount of change doesn't even depend on K.
So just by leaves, you mean the number of leaves of this?
The whole tree.
Or if you have, it's now broken up into several sub trees and stuff, the leaves at that stage, or
Yeah. So
some people who are ancestors at some point could have become leaves later on, or
yeah, exactly. Some people who had children could now become a leaf because so this is the forest of proclaimed true nodes.
okay.
The number of leaves in this thing.
Okay.
It didn't quite suffice, so we had to add like plus number of connected components or number of trees. And somehow this is, and in the other case, what did we do? We had to, so this when we had to try to prove the process is actually dying, you need to have a little bit more of an understanding. If you have very deep paths in this structure, it's going to be hard to kill because you're only checking K levels up. So anybody who comes and tries to attach at the bottom level actually dies, survives, and they continue. So if you really want to say that, oh, but I've set P and K pretty high, they should die, then you have to have some way of controlling these long, deep paths. We spent a lot of time trying to prove that preferential attachment will not develop such and such trees and so on. Nothing was kind of easy to analyze. It's really hard to understand the state of the of evolution of a preferential attachment tree, leave alone after we are doing all this damage with injection of errors and elimination of nodes. Instead, what we were able to do is some sort of an exponential potential in depth. So for each node, you put in a potential which is exponential in its depth from the root, and you just sum this up over all the nodes in the that are alive. Okay, and it turns out this actually, you can prove that this is shrinking for a while, and that's how we're proving the settings where things are shrinking. And finally, there was this one case where we said, oh, look, if you're checking exactly two levels up, then something that doesn't happen. There we were again counting something like the following structure. How often do I see this structure in the tree? Some node which has exactly one child. Okay, so if you see these kinds of structures, and there are many of them independent in the sense they don't share, one of these is not an ancestor of the other, that is a potential function that happens to grow when you're exactly checking two levels up. So a little bit of thing, I mean, these are unfortunately very ad hoc looking potential functions. There's one analysis for this case, one analysis for that case, one analysis for this case. It's not surprising that we're not getting matching results, right? So if you are really interested in probability theory and how these kinds of processes could evolve, I mean, there might be lots of very interesting questions to explore over here. And I think there's sort of a ton of open questions to be looked at.
So for meeting the thresholds, is it possible to do some sort of fluid limit analysis?
Come again?
Fluid limit analysis of this.
I don't know. I mean, yeah, I mean, I don't know enough of this thing. The probability experts over here were Elkanan and Dan. They are still, I think, not really sort of very familiar with the fluid analysis methods. So I expect there could be possibilities. There's a little bit more. I mean, I've seen fluid limit analysis applied to things in queuing theory and so on. There's a little less of the. I mean, this one is a little bit more of this tree combinatorial structure, which looks a little messy to me. But if you know something about it, maybe worth trying to pursue it. And by the way, let me stop the talk at this stage and open for questions.
Further question? So in situations like, when K was 4 or something where we knew that the tree does die, how much time does it take? I mean, like, is that something that can be quantified in terms of?
Lots of these things have been, I mean, phenomena like these have been quantified exactly. So one could ask the question. So of course, if I sort of start with the root and say, oh, how much time will it take to die? It's constant. So, but you can ask the question, suppose I start with a substructure of size n that somehow got developed. And now let's see how long will it take before it actually dies out. Is it polynomial in n, and exponential in n? Is it linear in n, etc.? And I think, okay, some of these things, I mean, when we can analyze that this process will die, I'm sure the potential function is telling us. So quite often this potential function says, okay, look, this potential function, so for instance, this exponential potential function actually shrinks by some sort of a constant factor almost at each time step. No, actually, that can't be right. Let's say, okay, it decreases by at least 1 per node in each time step for some constant. And so in a linear amount of time, you expect it to be down to some constant, etc. And similarly, when things are growing, we could ask the question, okay, it's growing. This is growing and that's growing. The conditionally true node, its subtrees are growing. Conditionally false node, its subtrees are growing. But this should be growing slower. Can you analyze the rate at which these things grow? Again, these are wonderful questions and we don't know. We don't have good answers for any of them.
Because I was just wondering, so there are these notorious sort of tree problems, like the Hydra problem that is there, which is like there's a weird sort of way in which, I mean, there's a tree and every time you remove a leaf, a certain thing happens where it looks like the tree is going to get larger and larger. But this process always terminates in finite number of steps. But usually these are situations where you have no bound on how much time it takes. So I was wondering if there was some similar situation that was happening here. The sense that the potential, it decreases, but you don't have a qualitative bound.
Our potentials are very explicit. So, but the thing is, okay, we will, these things, we know them very easily but they analyze very special cases or only some corner cases. They're not giving us a complete analysis. So that's the.
I mean, for example, this feels like something that one can just program and try out, right? Like what happens, like we just practically try this out. Like was 1/4 that you mentioned is 1/4 the right threshold?
Right, okay, that's a good question. I don't remember that we tried anything out in this case. For some strange reason, none of us coded this up. I mean, there was a previous paper that we were thinking about similar, gossip exchange and so on, in which we got a fair amount of intuition by coding it up and so on, but we didn't do it in this case. Yeah.
Further question? Back to the advisor thing. Columbia now insists every student has
Two advisors.
So by the way, that paper is coming up soon. Two advisors are worse than one. Thank you.